Good morning. I'd like to introduce you to the AURORA Retina antenna, the first iteration of AURORA prototypes developed by ATG Solutions. So as you can see here, our proprietary technology primarily lies in the Luneburg lens design that we've designed to perform well up to KU band. So that's what you see largely at the center here, covered by a 0.1 dB loss radome. So if we take this off, we would see the lens itself. Up here on either side, on either corner of this, we'll see differential GPS antennas for attitude orientation as well as a GNSS compass lock. Down here, you see our internal PC. This is running primarily Python for the whole application of what we're doing on the antenna. You see adjacent to it that we'll have our digital hookups for Ethernet ports all routed into a switch for external hookup as well as modem data. Over here we have HDMI and USB ports. We'll be utilizing the HDMI to access the user interface. Over here we have our KU band inputs and outputs. On the left side, you'll see that the AURORA Retina prototype has the capability for 8 receive channels. And for the sake of this demonstration, we'll be displaying 6. So the downlink for KU will represent 10.7 and 12.75 gigahertz outputs. Over here, you'll see that the prototype has the capability for 4 simultaneous transmit beams. For the sake of this demonstration, we'll be utilizing 2 at an uplink frequency of 13.75 to 14.5 gigahertz. Over here, we have our power distribution with our main power switch. The main power runs off of 24 volts that is then routed throughout the whole system through various conversions and regulators. And we have auxiliary power should the main power current limit of 25 amps be exceeded. Down here we have our power amplifier voltages. So we'll be supplying 24 volts into TX1, which is then up converted through a series of Vicor boards, up to 28 volts that is then routed into the power amplifier. And for the subsequent transmit beams, we'll be directly supplying that 28 volts. So as we look over here, we can see more heat sinks and fans. These are all associated with power amplifiers through our smart cooling system. For the AURORA Retina demonstration, we will be displaying 6 tests. That will be 6 receive beams for Retina as well as 2 transmit beams. So for our first 3 tests, we'll be utilizing our Pseudolite infrastructure up on the manlift at a height of 65 feet. That is well within the elevation range of Retina. Our first test will be shooting at the transceiver in the upper right hand corner of the man lift. We'll be transmitting a modulated carrier from Retina up at 14.125 gigahertz, and the transceiver will be translating that down to 11.835 gigahertz into Retina, and we'll be displaying that modem lock up on itself on a CDM 625. For the second test, we'll be doing a similar thing at a slight frequency offset into the lower left-hand corner. We'll be coming up at 14 gigahertz, and we'll be coming back down to 11.7 gigahertz. For the third test, which will be our final test on the man lift, we'll have a transmit-only horn in the upper left-hand corner, and that will be transmitting down at 11.95 gigahertz into Retina, and we'll be displaying that modem lock as well. For these first 3 tests, we will be displaying local loopbacks on CDM 625 modems. These modems have an L-band input and output, so we will be using bucks and LNBs to upconvert and downconvert for Retina KU capability. We'll be displaying each of these modem locks on the user interface, and we will also be displaying the spectrum that is picked off at a power splitter that it will be switching through these 3 using modular test system. For our 4th test, we'll be showing a geosynchronous satellite lock, and we'll be doing this receiving Telstar 14R using our CDM 760 modem rack. The downlink carrier will come in at 12.027 gigahertz, and we'll be displaying that using our spectrum analyzer, Signal Hound. we'll be showing that modulated carrier. For our fifth test, we'll be doing another geosynchronous satellite receive chain. For this one, we'll be receiving EchoStar 14, which has reception with Dish Network. So this is a Dish receiver. We need to use this for initial lock on the TV. However, once we flip over to the Retina receiver, then we will use this coaxial switch to cut over and show that we maintain television lock through Retina. And we'll be using this Field Fox spectrum analyzer to show 10 carriers between 950 and 1450 megahertz in L-band. For the sixth and final test, we will be tracking a OneWeb LEO satellite across the sky. And for all 6 of these tests, we'll be showing them with simultaneous lock.
Hello, my name is Francis Forrest. Now that you've been given an overview of the Retina Antenna System and the equipment that we will be using today for the demos, we're now going to shift to the user interface and actually walk through each one of the demonstrations. And while we do that, I'll be showing you different screens on the user interface. And Luke will be running that operation for us. And we will be showing with each demonstration what it looks like on the test equipment as well as the results on our modems. The Retina user interface has 4 main sections to it. We have a dashboard screen, which gives you an overview of each of the areas of interest for the system. GNSS status, that gives you the geolocation information, attitude of the INS system, which is monitoring inside of the antenna system. And as each channel or each beam is turned on, that in our demonstration, that will give you the activity state in the next section here. We do have some override features as well, where if the antenna system is stationary for a period of time, we could override it with our current position as well as the attitude and lock that in case you are in GPS denied region. This will be of benefit. The next section that we will be talking about is the entity configuration screen. This is where we will set up each one of our entities, whether it be satellites or pseudolites or terrestrial. And then after that, we have the terminal configuration screen where we will direct the RF signals, where they originate and where they will exit the antenna system into the rest of the equipment. And then we actually have an antenna visualization screen, so you'll actively see the beam that's currently active, as well as the feeds that are generating that beam and the direction of the beam itself. On the entity configuration page, we will set up one of the pseudolites for the first demonstration. This will be for Pseudolite TX-RX1, as it's up on the man list. We begin by entering the name of the entity itself, and then we give what type of profile it is. Is it a LEO, MEO, GEO, or terrestrial entity? So that will be next. We've selected terrestrial for this device because we are local on a man lift. And then the position data, this is where the data has been preloaded into the antenna system, where it is imported. We use NORAD as one of the sources of the TLE data, or the user could import this data if they have a specific pattern or location status that they're going to be using for their device, or other user-defined entities, location of the data. And then you enter the azimuth and elevation of the entity, where it is relative to the antenna system itself. We do have a calculator within the Retina user interface system that we could enter in the geolocation data, and it will generate the azimuth elevation that's needed to be entered here. Once that is completed, we submit it, and it will store this information for future. As you see on the entity configuration, it has saved this to one of our options. Now on the terminal configuration page, this is where we take this entity and we assign either a transmit port or receive port that the RF will be either going into or out of. And then it will take the information from here and we'll turn the beam on from here. So once we select it, now we enter in which port it's going to be directed into, the frequency of operation, the input power level that we have, and then the desired EIRP. On the receive side, we select the receive port, the frequency of operation for that as well as the maximum number of feeds that we want to contribute to this receive. Turn the status on, that will turn the beam on. As mentioned in this first demonstration, a transmit signal is sent to the Pseudolite, and then it is down converted and sent back as a loop back to the retina antenna system. So what we're seeing now is the return signal after it has gone through in L-band. Switching back to the modem status, we see here that the bit error rate remains at 0. So we have a good loopback system without errors. For the second demonstration, we've already pre-configured the entity, so we will now just go to introducing it into our terminal configuration and defining which ports, as we see here. This second demonstration is going to be going on while the first demonstration is currently active. So we already have one beam active. We'll be turning on the second beam, and this demonstration is of a second Pseudolite that's on the man lift. So that has been turned on, and we can look at the spectrum output as well. Looking at the spectrum analyzer, we can see the modulated carrier that's being received and down converted to L-band. Looking at the modem screen for this demonstration, we also see that the bit error rate is 0 and maintaining 0 throughout this loopback, as well as the continue to be 0 on the first modem that we set up. Making use of the antenna visualization page of the user interface, we now are showing two beams. The first demonstration is this color where the feeds that are being used are lit up. The crosshairs represent the direction that the beam is facing. And this is for the demonstration 2 that we just set up, and it's also going simultaneously to the Pseudolite. For the third demonstration, while demonstration 1 and 2 are still active, we'll now look at the receive beam from a third satellite that has the L-band feed going cabled up to the horn on the man lift, and it will transmit a signal back down to the antenna system. So that has been set up, and now we just need to turn that on. We'll have 3 beams, and if we look over to the visualization page, we now have that beam active as well. So 3 beams simultaneously activated. And now we'll look over at the spectrum. Here are the results of, this has been downloaded to L-band, and this is the modulated spectrum that's being generated through the modem. Now let's take a look at the modem lock for this demonstration. You see here that the bit error rate is also held at 0. And monitoring the first modem, that lock has stayed on, and the bit error rate is still 0 for that, as well as for the second demonstration. So all 3 beams are on, they're locked, and with 0 bit error rates. Beginning this fourth demonstration, we will use a modem that's remote in New Jersey, and it's connected to an 8.1 meter antenna that is pointing to Telstar 14R. Telstar 14R is then sending the signal down to the retina antenna system, which we will now activate the beam to receive that signal. This has been pre-set up in the interest of time, but then we see on the display that received signal. On the visualization page, we now have 4 beams that are being received. These are the feeds that are associated with them, and again, the crosshairs represent the direction that the beam is going out of the antenna system. Okay, looking at our local modem, you see that the bit errors are 0 and we're locked onto this satellite. Now what we will do is remotely access the modem that's in New Jersey, and we're going to insert an error into that, and we're going to see that error show up on our modem here. The error was inserted, it's now detected on our system. And as you notice, it's very stable, and it remains at just that single error throughout this test. Well, the first 4 demos are active. We'll now do the 5th one. The 5th one involves a dish TV reception that we're receiving from EchoStar 14. And that has been configured in the entity configuration page, and now on the terminal configuration, we will just turn this beam on. Looking at the antenna visualization page, you'll see that we now have 5 beams. We have the first 2 that are transmit and receive simultaneously, full duplex, as well as the other 3 receive only ones. And now EchoStar 14 that carries the dish TV broadcast is now on this readout as well. This is a down-converted spectrum from retina of the dish broadcast. And now sliding the switch over, we will now go from the dish receiver to retina's receiver and view the broadcast. Looking at TV monitor, we are looking at the dish broadcast from the tailgater antenna system, and now we will cut over to the retina antenna. And now we're viewing the reception from the retina antenna. Checking back on our modems from the first 4 demonstrations, looking at modem 1, we notice that the bit error rate remains 0. Modem 2, bit error rate is also 0. Number 3, also 0, staying locked. And the 4th one has not picked up any more errors from the one that we initially intentionally put into it. So looking up at the antenna visualization, we'll now have all 5 receive beams and 2 transmit beams currently locked. Turning to our last demonstration, we'll now show you tracking a LEO satellite. So we have one selected here, the OneWeb satellite. We'll take the one that's closest overhead and turn that receive beam on using the TLE data on its tracking trajectory. It's turned on. Now on the antenna visualization page, we're looking at this one, which is this red one. You can see it's currently tracking. This is the beam moving, and this is the beam itself at the output of the antenna, azimuth, where it's tracking that LEO. So now we have all 6 demonstrations running simultaneously, ending up with 6 receive beams and 2 transmit beams simultaneously. Looking back at the dashboard of the user interface, everything's still locked up, And now looking at the antenna channel status, we'll see that all 6 entities are being displayed. The 2 transmitters show their actual EIRP, and everything remains stable.